Welcome back. We are talking about the secondary treatment of wastewater treatment. In this video, we will be talking about the design example for the plug flow aeration systems. Is also called as conventional accurate sludge process, or by looking at the simple example, the process of the diffused aeration systems. So now the design diffused air accurate sludge process per 1000 meter cube per day of sewage flow when a BOD of 300 milligram per liter is entering into the system, and 30 milligram per liter of BOD should leave the system. So you assume the suitable data. So now when you are starting the design, you should know the design parameters. All the design parameters are given here at the bottom. For each of the accurate sludge process mechanisms, we are having a set of parameters. The set of parameters are different. So we have to use these values in calculations. So starting value, I'm assuming here MLSS, X is equal to 3000 milligram per liter. And then the volatile suspended solids, MLVSS, is organic fraction or a volatile fraction of that, which is around 80% of MLSS. So 80% of 3000 is 2400. And HRT is hydraulic retention time, I'm assuming as 6 hours. And to start the design, we should go for the BOD removal efficiency, whether the system is perfect or not. This is suitable to the given example or not. So how much BOD is removed? Initial to the outlet value. 300 minus 30. Initial value is 300. So 270 by 300, that is 90%. The BOD removal range for this process is 85 to 95%. So that means this process is satisfied. Now we go for the BOD loading. So how much BOD we have? How much BOD we have applied here? That is Q into Y naught minus YE. Q into Y naught minus is also written as Q into YE, neglecting YE. When the inlet BOD is very high and the outlet BOD is very small. But here 300 to 30 is a reduction and flow rate is 1000 meter cube per day. So applying all the corrections, it comes out to be the 270 kg per day. So this is actual. If you neglect the YE, so it is equal to 300 kg per day. You're talking about the volume of the tank, how to calculate here. So now the discharge is equal to volume by time. We know that. The volume will be equal to discharge multiplied by time. So Q is the discharge and HRT is the time you have taken 6 hours. Multiply that, you have 250 meter cube. So then we calculate volumetric loading. That is how much of BOD is applied per unit volume. So Q into Y naught by V. So 300 is the kg per day, the maximum load applied. 250 is the volume and is equal to 1.2. So slightly higher than the range given here. Doesn't matter. And now F by M ratio, Q into Y naught by Vx. This is nothing but Q into Y naught is the food. Food is nothing but the BOD which is there in the system. And Vx is nothing but the microbial mass system. In the microbial mass calculation, there are two things. MLSS consists of both inorganic as well as volatile solids. So MLVS is considered only the volatile solids. Volatile solids are often considered as the active biological solids in the system. So whenever we talk about the microbial mass, we always consider in terms of MLVSS. So now let us calculate in terms of both. It doesn't make much difference. So I considered it in terms of MLSS as 3000 milligram per liter in terms of MLVSS 2400. For MLSS, I got zero point 0.4 here. For MLVSS, I got 0.5. The standard value, whatever is given here, is in terms of MLSS. To calculate recycle ratio, we require sludge volume index. So we assume SY sludge volume index is equal to 100. So the solids concentration, the recycled sludge concentration is given as 10 to the power of 6 divided by SPI, which is equal to 10,000 milligram per liter. The recycle ratio is written as QR by Q, which can also be written as Q by XR minus X. So here MLSS. So remember always MLSS is represented as X, MLVSS as XV in this example here. So 3 divided by 7 is the R value equal to 0.43. This is less than the 0.5, the maximum limit. It's okay. So recycled flow will be equal to QR into Q, that the R into Q, 0.43 into Q here. So 430 meter cube per day. Sludge wasted, we have to calculate. Sludge wasted is expressed in terms of QWXR. So to calculate a QWXR, we have to go with the formula SRT is equal to Vx by QWXR. SRT is equal to Vx by QWXR. So SRT we have to assume here. The SRT value in the design is given as 5 to 15 days. So I'm assuming 10 days here. So V is known, X is known, XR is also known, 10,000 milligram per liter. So now I'm calculating QW. QW is coming out to be 6 meter cube per day. So QWXR is equal to 6 meter cube per day into 10,000 milligram per liter. So apply the conversions to convert milligram to kilogram and liters to meter cube. Finally, I'm getting here 60 kgs per day. Whenever we talk about the biological treatment system, we also need to talk about the growth yield coefficients. So growth yield coefficients, they are giving the efficiency of conversion in the biological system. So the formula given here is XV into HRT, XV into HRT into 1 plus KD SRT is equal to SRT into Y into S0 minus SC. So here S0, this is the formula. S0 is soluble influent BOD, which is equal to 5-day BOD, 300 milligram per liter. SC is the effluent soluble BOD. And to calculate the soluble effluent BOD, we need outlet suspended solids. Normally, the outlet suspended solids will be around 20 milligram per liter. Very small value you're going to get. And from that, the BOD of effluent solids you can calculate. So this is 63% of the effluent solid, 12.6. Soluble effluent BOD will be equal to outlet BOD minus this BOD of effluent solids. So this is the soluble portion. This is the insoluble portion. It is 17.4 milligram per liter. So difference of S0 minus SE in terms of soluble BOD is 282.6. So now the KD value we have to assume. This is a rate constant. The rate constant we can assume as 0.05 as per the standard data and calculate the value of Y, which is 0.32. So the range is 0.4 to 0.8. So very close to the range. All these checkpoints are helpful to understand whether the values are overrated or underrated or the assumed values, underrated or overrated or within the range. To calculate the oxygen requirement, first of all, we should calculate the ultimate BOD from the 5-day BOD. To calculate the ultimate BOD from the 5-day BOD, we need to multiply with 1.47. Because some solids are wasted, QWXR, that should be deducted. So there is a conversion factor in this. We are using 1.42 with respect to sludge wasted. And this is the net oxygen requirement we are going to calculate, which is actually requiring oxygen in the treatment system. So QWXR already we know that 60 kg per day, and Q into Y naught minus Y, the BOD loading is already we know 270 kg per day. And you put everything here, you're going to get 312 kg per day. The air requirement, because diffused air system requires a compressed air. So that means we require the compressed air to be calculated here. To calculate air from the oxygen, we need to go with the fundamentals. 23% of oxygen in the air and the specific gravity of air as 1.2 kg per meter cube. So air required, we are going to calculate from this. Once we calculate amount of air required, and assuming 100% extra air due to probable clogging in the diffusers, and the 1130 is the air required, and then you're taking 100% allowance, it comes out to 2260. The core diffusers we are assuming with a 6% efficiency, and then air required will be with respect to that 6% efficiency is 37,606 meter cube per day. So air requirement also we can check with respect to BOD removed. So usually it should be on not more than 100, slightly higher, doesn't matter. Too much of loading will create a problem for the bacteria. There's only reason to look at this here. And diffuser plates. Air required we already calculated 37,666 meter cube per day. So in terms of minute, it is 26.16. Standard diffuser plates are 0.3 meters by 0.3 meters by 25 mm. So plate area is 0.3 into 0.3, 0.909 meter square. So the standard data gives you this will supply 1.2 meter cube per minute per meter square of compressed air. So how much diffuser is required? 26.16 is the requirement, and 0.09 is the area, and 1.2 is the meter cube per minute per meter square. You multiply these two and then divide with this value. So from this, you are getting a 242 number of diffusers are there. So tank dimensions, now let us calculate. So 250 meter cube is the volume. Let us assume depth is equal to 3 meters. And let us assume B by H is equal to 5 by 3. We can also go up to 2, doesn't matter. But some intermediate value are taken here, 1.67. Accordingly, I calculate the length as 17 meters. Number of diffusers are 242. So now we have to plan how to put these diffusers. Put 8 rows so that 30 in each row, and leaving 0.5 meters on either side. The length 17 meters, 2 into 0.5 is 1 meter, 17 minus 1 is 16 meters. And then put some spacing, calculate here 0.5 meter spacing. And spacing between the rows also we can calculate 0.5 meters. So now finally this is what you are going to see the requirements. 17 meters is the length of the tank, 5 meters is the width, and there will be 8 number of the diffusers, rows, 30 diffusers in each row, and 0.5 meters spacing. This is the spacing, 0.5 meters. And there will be some spacing between these two rows also. So that is 0.5 meters. Now is the picture you can see in this This is how the diffusers are going to be arranged. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 rows here. The 12 rows here, and number of diffusers are there. Now in the bottom picture you can see the diffusers are placed here, some center to center distances. So here the circulars are there, but what we are taking is 0.3 meters rectangle square sections. So this is how we come out with the dimensions of a standard plug flow aeration system, are also called as conventional aeration system, is also called diffuse aeration system. Now you can see here, this is the pictures on the right hand side. They are showing how the water is mixed because of the diffusers from the bottom. So they are not completely mixed as in the complete mixed process. No, they are mixed in separate pockets. That's what you can observe. That's what you can observe here in the pockets. See, this is one pocket, this is another pocket, this is another pocket. These pockets are corresponding to the air coming from the bottom, right? And what you see in this picture, you can see the very long tanks are there, and this is the width. This long tank, 17 meters, we are talking here. This is 5 meters, and 3 meters is the depth, right? So this completes the design of the uh, diffused aeration process, or standard or conventional aeration system.